Okay, so we got a request to take a deep dive into some really cool research on quantum cryptography.
Totally fun.
Yeah. It's a paper called The Quantum Cryptography Approach, Unleashing the Potential of Quantum Key
Okay.
by these two researchers, Neha Sharma and Vika Saxena from the JP Institute of Information Technology.
Interesting.
And basically, they found a new way to generate and transmit secure keys
Oh, wow.
without revealing the sender's method at all.
That's huge because, traditional Qiskit quantum key distribution, I mean, it makes a lot of assumptions about the devices being perfect and all that. Obviously, in the real world, devices aren't perfect.
Right.
And so that causes some problems.
So trying to get around that and be more secure.
Exactly. Yeah, they're trying to make it more realistic so that it's more applicable to actual situations.
I see.
And the coolest thing is that the sender, we'll call her Alice, never reveals her encoding basis.
Oh, wow.
Even Bob, the intended recipient, doesn't even know it.
So how do they make sure that they're on the same page then if they're both in the dark?
Right.
About the encoding method.
Well, that's where their innovation comes in.
Okay.
They use this thing called polynomial interpolation to verify the keys.
Polynomial interpolation?
Yeah.
I vaguely remember polynomials from high school, but
yeah.
I don't really know how.
It's a little bit like a mathematical fingerprint.
Oh, okay.
Of the code.
Gotcha.
So imagine Alice arranges her key bits into a grid, like a matrix. Each row of the matrix represents a set of bits.
Okay.
And she converts chunks of those bits into decimal numbers.
So she's making it more organized.
Right.
Yeah.
More structured.
Okay.
Now for each row in the matrix, she generates a set of random decimal numbers, and those are like the y coordinates. And the decimal numbers from her key bits become like the x coordinates.
So she's using coordinates.
Yeah, like plotting points on a graph.
Oh, I see.
And with those coordinate pairs, she can construct a polynomial equation.
Oh, okay. So connecting the dots to make like a line.
Exactly. It's like a curve.
Okay, a curve.
Yeah, and then Alice sends those y coordinates, those randomly generated ones, to Bob. If Bob has the same key bits, he should be able to reconstruct the exact same polynomial using his key bits as the x coordinates.
So they're both kind of making the same curve without knowing what the other one's doing.
Exactly.
Oh, that's cool.
And the magic lies in comparing the coefficients of the polynomial.
Okay.
So if they match, then that confirms that they have the same key.
Without giving away the secret.
Exactly.
That's pretty clever.
It's like a double check.
Yeah.
Without actually revealing what the key is.
I like it.
So any mismatch indicates either an error in the transmission or potential eavesdropping.
Oh, so it's a way to see if someone's listening in.
Exactly.
Yeah.
So they put this to the test.
They did.
They simulated the protocol on a quantum computer using IBM's Qiskit platform.
Oh, cool.
And in their initial simulation with 7 qubits, they found that in a perfect noise-free environment, Bob's measurements for common bases always matched Alice's bits.
Okay, that's promising.
Yeah.
But like you were saying before, a noise-free environment is not really realistic.
Right, that's the ideal scenario.
Yeah.
They didn't just stop there.
Oh, good.
They introduced simulated eavesdropping and various types of noise to see how their method holds up in more realistic conditions.
Okay, so they brought in the bad guys and shook things up a bit.
Exactly.
I like it.
Yeah, to make it more challenging.
All right, before we get into that, what were the different types of noise that they were working with?
So they were working with 3 main types.
Okay.
Polygate noise, depolarizing noise, and measurement noise.
Okay, and all those mess things up in different ways.
Exactly. Yeah, it's kind of like static on a radio.
Right. We've talked about that before, how noise can be such a problem.
Huge.
In quantum computing.
Yeah.
So what did they learn about these different types and how they affected things?
Well, as you might expect, all 3 types of noise decrease the probability of Bob receiving the correct key.
Right.
But the impact of depolarizing noise was particularly interesting.
What was so interesting about that one?
Even under the most extreme conditions, like maxing out the simulated depolarizing noise, there was still a chance that Bob could receive the correct key.
Oh, wow.
It never dropped to 0.
So even with all that noise, there's still some hope.
Yeah, exactly.
Bingo.
And this is where the research gets really interesting.
Okay.
Is how this method performs under pressure.
All right. Let's get into it.
Let's do it.
I'm hooked. So they actually simulated eavesdropping to test this.
Yeah, they basically introduced the eavesdropper into the system.
The bad guy.
Exactly.
Okay.
And they did this by randomly measuring parts of the quantum circuit, essentially simulating Eve trying to intercept the key.
So she's like messing with the qubits.
Right, as they're being transmitted.
Yeah.
And they varied the strength of Eve's interference to see how it affected the error rate in Bob's key.
That makes sense. So like the more Eve interferes, the more likely there'll be an error.
Exactly. And what they found was really interesting.
Okay.
As Eve's interference increased, the percentage of errors in Bob's key also went up.
Okay.
But here's the key thing.
Yeah.
If the error rate exceeded a certain threshold, the protocol would just restart.
Oh, that's smart.
Preventing the use of a compromised key.
Yeah, like a self-destruct.
Exactly.
Right.
Yeah. It's all about making sure that they only use a verifiably secure key.
I like it. I like it.
And they also looked at how each type of noise affected the success rate of the protocol.
Right. We were talking about the polygate noise and the depolarizing noise.
Yeah, all those.
Yeah, and the measurement noise.
Exactly.
So what did they learn about those and how they affected things?
So, as you'd probably expect, all three types of noise, they decrease the probability of Bob getting the right key.
Right.
But the impact of depolarizing noise was really fascinating.
Oh, what was so special about that one?
Well, even in the worst-case scenario,
Oh,
with the maximum simulated depolarizing noise, there was still a chance Bob could get the right key.
Really?
The success rate never hit 0.
Oh, wow. So there's still hope.
Exactly, even with all that noise.
Yeah.
That's one of the really cool things about this method.
So it's pretty robust.
Yeah, it seems to be more robust than some existing QKD protocols.
Okay, that's a big deal.
Yeah.
But I mean, all of this is simulations, right?
Right.
Like, how practical is this, really?
That's a great question.
Like, can we actually build quantum devices that can do this kind of cryptography?
Well, that's one of the biggest challenges facing quantum computing right now.
Which is
scalability.
Scalability. What does that mean in this context?
So right now we're running these simulations on a pretty small number of qubits. But to make quantum cryptography practical for the real world, you need to scale up these systems to handle way more data, so you need lots more qubits.
So it's like we figured out how to make a brick, but we don't know how to build a house yet.
Yeah, that's a great analogy.
Okay.
It's like trying to build a skyscraper with just a few bricks.
Right.
Scaling up any quantum system is a huge engineering challenge.
Yeah. What are some of the biggest hurdles researchers are facing when they try to scale this up?
Well, one of the biggest ones is entanglement.
Okay.
You need to maintain entanglement across a lot of qubits.
Right.
And entanglement is really fragile.
Yeah.
It's easily disrupted by noise and decoherence.
So the more qubits you add, the harder it gets.
Exactly. It gets really messy.
Right.
And then on top of that, you have the whole issue of controlling and managing all these quantum devices.
Oh, yeah.
You need some super sophisticated algorithms and hardware to handle all that data.
Sounds really complicated.
It is. It's cutting edge stuff.
Yeah. It sounds like we're still in the very early stages of figuring all this out.
Yeah, we are.
But, I mean, people are working on it, right?
Oh, absolutely. There's a ton of research going on right now and
Right.
some really promising developments.
Okay. What are some of the most exciting breakthroughs that you're seeing?
Well, let's talk about those.
Okay, so we know scaling up is a big challenge for quantum cryptography. Are there any, like, breakthroughs or new ideas that could help us overcome these hurdles?
Yeah, actually, one area that's really promising is the development of quantum repeaters.
Quantum repeaters, what are those?
Basically, they can extend the range of quantum communication,
Oh, wow.
so we can build larger and more robust quantum networks.
Okay, how do they work?
They kind of act as intermediaries between entangled qubits,
Okay.
like relay stations along a quantum communication channel.
Oh, I see.
So they can amplify and purify entangled signals, counteracting the effects of noise and distance.
So they're like signal boosters for entanglement.
Exactly.
Well, that's cool. That's really clever.
Yeah. It's a game changer for building these large-scale quantum networks.
Right. We need those if we're going to make this practical.
Yeah, for sure.
Are there any other cool developments happening?
Yeah, definitely another exciting area is the development of new QKD protocols.
Oh, new protocols,
Yeah.
like better than BB84.
Well, they're exploring different approaches
Yeah.
that might be more practical for the real world, especially as we try to scale these systems up.
It's really cool to see how much innovation is happening in this field.
Yeah, it's super exciting.
I mean, people are working really hard to make quantum cryptography a reality.
Absolutely, it's moving fast.
Yeah, and we talked before about how there are ethical considerations, too.
Right, we can't just focus on the technical stuff.
Yeah, like what about misuse and privacy and stuff like that?
Exactly.
Yeah.
It's super important to think about those implications.
Yeah, because this technology could be used for good or bad.
Right. The same technology that protects privacy can also erode it.
Yeah, if it falls into the wrong hands.
Yeah.
That's kind of scary.
It is. It's a big responsibility.
So how do we make sure it's used for good?
Well, it requires a multifaceted approach.
Like what?
We need clear guidelines and regulations, international cooperation, and a strong commitment to ethical practices.
Yeah, within the quantum community.
Yeah, exactly.
It's like we're building a whole new world here.
Yeah, it's uncharted territory.
Yeah.
And we have to be aware of both the potential benefits and the potential risks.
Speaking of risks, Sharma and Saxena mentioned exploring attacks on discrete systems in their research.
Yeah, that's a key part of making these systems secure.
Yeah. So what kind of attacks are we talking about?
Well, one category is side-channel attacks.
Side-channel attacks.
Yeah.
So these attacks, they don't try to break the algorithm itself.
Okay.
They try to exploit weaknesses in the physical implementation of the system.
So like the hardware or something.
Exactly, like trying to find a back door.
Oh, so they're being sneaky. Oh, yeah. They might try to measure the power consumption of the device or analyze its electromagnetic emissions.
So they can figure out the secret key.
Right. It's all about getting information.
Without directly attacking the algorithm.
Exactly.
That's so clever, but also kind of terrifying.
Yeah. It shows how important it is to have strong security measures at every level.
Right. Not just in the math, but also in the actual physical devices.
Exactly.
What other kinds of attacks are there?
Well, there's also quantum hacking.
Quantum hacking, so using quantum tech to break quantum cryptography.
Yeah, it's kind of a quantum arms race.
Oh, wow.
As quantum cryptography gets better, so do the attacks.
So it's a constant battle.
It is. It's like a game of chess.
Trying to stay one step ahead.
Exactly.
Well, this has been a fascinating deep dive into the world of quantum cryptography.
Yeah, it's a super interesting field.
Lots of challenges, but also lots of potential.
Yeah, tons of potential.
It's really exciting to see where this technology will go.
Yeah, for sure.
And what kind of impact it will have on our lives. Yeah, absolutely. Well, I want to thank you for taking the time to break all this down for us.
No problem. It's been a pleasure.
Until next time, keep those brains buzzing.
For sure.
The quantum world is full of wonders.